Welcome to lecture 40. This lecture I want to talk about inflation. Recall that we have studied the evolution of the scale factor in the FLRW universe. The solution depends on the matter content of the universe. By matter content, we mean matter in general terms, including dark matter, radiation, as well as dark energy terms. So far, we have mostly focused on solutions that were dominated by matter or radiation, but not so much about dark energy. So in this lecture, we want to focus on the contribution that dark energy plays in the evolution of the universe. To set the stage, I want to revisit a key problem of cosmology. This is known as the horizon problem, and it is formulated most easily in the following way. Shown here is a map of the galactic sky in all directions from the WMAP probe, and this is known as the CMB, the cosmic microwave background. It is simply the radiation that reaches us from all directions in the sky. We've taken out planets and galaxies and things like that, so they don't distort the picture. And what is shown here actually is the differences blown up by a factor of 100,000. So if you were to look at the sky in the infrared, you would find that there are small differences. There are sort of higher temperature regions such as this and lower temperature regions, but these regions here are small compared to the overall background. So all of these fluctuations are fluctuations that are suppressed by 5 powers of 10. So overall, it looks extremely smooth across the whole sky. And the question is simply, well, how does a photon that's coming in from this direction in the sky know exactly to have the same temperature as a photon that's coming from the precise opposite direction of the sky? These two photons cannot have been in causal contact. So basically, how is it possible that they have the same temperature? This is known as the horizon problem. So in order to focus on this, let's review some of the main building blocks of cosmology that we've discussed in this lecture. In particular, the Friedmann equations, and we have found solutions to the matter part of the Friedmann equations, such that we found an energy density epsilon of t given in terms of the scale factor A of t, where the equation of state, which is the matter content that we sort of assume, is encoded in this parameter w. So to find a solution of the scale factor, we have to sort of plug this solution into the equation 40.2, where here this is the Hubble function, and kappa is the curvature term that can take values -1, 0, and 1. So now let's look for solutions to these two equations, assuming pure dark energy. So to do this, let's assume that there's no matter, not even dark matter, and there's no radiation in the universe. What would happen? All there is a cosmological constant, which I call dark energy. Pure dark energy has an equation of state P is minus epsilon, so W is equal to -1. And the solution equation for our energy density then simply becomes that the energy density is a constant. If we plug this into the evolution equation, we find that the Hubble function then is a constant minus kappa over the scale factor squared. And if we use the definition of H is A dot over A, the evolution equation for the scale factor then is given in equation 40.5. If the scale factor A is much, much larger than 1, then basically this term here will dominate over the curvature term kappa, and we can neglect this curvature term kappa here. If this is the case, we can take the square root of this equation. There will be two solutions, one with a plus and one with a minus. Assuming that we want to describe a growing universe, we'll choose the plus solution here, and we can directly integrate this differential equation to find a solution for the scale factor, which is given as e to the t times a constant. So what we find if we assume pure dark energy is that the scale factor increases exponentially as a function of time. This exponential increase of the scale factor is known as inflation. The universe is expanding so rapidly that even light cannot compete. So space is expanding exponentially fast, and everything gets smoothed out. All the differences that were initially, because the space is expanding exponentially, get really decreased to very, very small levels. So overall, the universe will look very homogeneous and very isotropic. Because of these particular properties, this inflationary period solves two problems in cosmology. On the one hand, the flatness problem, which is that we find observational data suggests that the energy density in the universe today is almost one, so the universe is almost flat. And the horizon problem, which was the problem that I outlined earlier in this lecture, that says that how do photons from different directions of the sky basically sort of look like they came from the same temperature path. Inflation sort of tells us that the reason for this is because they came from the same temperature path, they were in causal contact much earlier, but then the universe was just blown up to imaginably large proportions because of these exponential inflation area. So inflation today is considered a key component in standard cosmology. There is no standard cosmology without inflation today, and it is key to sort of all of our understanding of interpreting observational data. However, I wanted to point out that there are also some problems with inflation, and I'll focus on two of those. So one of the biggest problems is that we have currently no means of actually calculating any properties of this dark energy. We can't calculate the cosmological constant. There are proposals for dark energy that are not in the form of a cosmological constant per se, but some other form of dark energy. None of these sort of really are viable calculations at this point, in the sense that they can't really match to anything that would be observable or theoretically justified. But in addition to this, there are some other problems that I want to mention. So first, consider the case that the cosmological constant is larger than zero. This was the case that I outlined before. In this case, we have a positive energy, and the curvature constant, if it's linked to the cosmological constant, is also positive because lambda is bigger than zero. So we find that the evolution equation is given by precisely the same equation that we had before. And we said that this gives our inflationary phase if A is much, much bigger than 1. And that's perfectly fine. However, if A is very large very quickly, then it was much, much smaller at earlier times. In particular, we find that if it's much, much smaller, then if A falls below a certain minimum size here, such that the right-hand side of this equation is smaller than 0, then suddenly this equation doesn't make any sense anymore. So we find that in this scenario, this inflationary scenario, there is a minimum size of the universe that's given by this quantity here. If we now change gears and say, oh, but wait a moment, observations actually tell us that kappa is negative, so kappa should be -1, then this would imply that the cosmological constant is 0 if we again assume pure dark energy universe. So in this case, the energy density is also 0, and our evolution equation is the same as before, except that the right-hand side has changed sign. Now in this scenario, there's actually no inflation at all because A cannot be very big. It actually has to be limited by that same minimum value that we had before. Now it's a maximum value. And it doesn't undergo inflation at all. In fact, if you solve this equation here, the evolution of the scale factor looks like this. The universe starts growing linearly, reaches a peak, and then starts to contract again and falls back and collapses back to 0. And we can, there's this point where the universe basically collapses back into a singularity is known as a big crunch. And this particular scenario has two things. It has a big bang here, and a big crunch at the end, both of which are set by the value of the cosmological constant. So this concludes my discussion of the inflationary period, assuming pure dark energy.